Now we're going to do the contribution due to V3. So here we set the switches to 0 for B1, B2, and B4. And then we connect switch B3 to V3. So now we're just looking at the current or voltage contribution due to V3. So again, as we did in the previous video, we're going to redraw this circuit. Again, we're going to see what this contribution of V3 is. So here we have Vx I labeled, and I labeled this as V3 prime because this will be the input to this inverting amplifier or summer. So redrawing this circuit, we have connected at the other end of this 2R resistor is Vx as shown here. Now we're going to take a look at this leg right here. So that's connected to R, and what's connected to R are these 2R resistors, two of them, 2R here and 2R here. And you can see this 2R is due to V4 connected to ground, shown here and shown here. And then this 2R is connected to ground as well. So that's this part of the network drawn. So that's right here. And now we see what's connected to the other end of Vx of this R resistor, and that's V3 prime. But V3 prime is connected to resistors, one connected to 2R, which is connected to ground, and that's because V2 is connected to ground right here. And then connected to the other end of this resistor R is the virtual ground node A. And so therefore this is the equivalent drawing of this circuit right here. Now let's, like we did in the previous video, can now calculate the equivalent resistance. So we have 2R in parallel with this R, which is really 2/3 R. But this 2/3 R is connected in series with this R, so that's what this calculation is. So R plus 2/3 R is equal to 5/3 R. So this 5/3 R is now connected in parallel with this resistor network. But we know that 2R and 2R is R, but it's in series with this R, so the net result circled in red in here, this dashed line circle, is simply 2R. So this 2R is connected in parallel with this 5/3 R. Doing this algebra, that yields 10th 11th R, or 10 over 11. Now we know that this resistor network is all equal to 10 11 R, all shown here. Now we can use the voltage divider to calculate first of all Vx and then V3 prime. So for Vx it's 10 11th R over 2R plus this resistor network equivalent of 10 11 R times V3. And that turns out to be 10 over 32 V3, or 5/16 V3. Now V3 prime, now we use Vx for that as an input to this resistor network, and now we can calculate V3 prime. And we could see that V3 prime is the input to this inverting amplifier. So V3 prime is just basically 2/3 R, that's due to this guy, and we know that this here is 5/3 R we shown earlier. So this is just a voltage divider of 2/3 R divided by 5/3 R, the sum of those two, of 2/3 R plus R. So we know that Vx we just found is 5/16 V3. So 5/16 V3 times 2/5 R. And that reduces to V3 over 8. We're getting that same pattern that we talked about earlier. So that concludes that analysis for the contribution of V3. Now V3 is simply, there should be a R right here. So let me rewrite that. V3 divided by 8R. Forgot to put that resistor. Because of the time, we're going to do the contribution due to V4 in another video, and after that video that will conclude the analysis of the digital to analog conversion for this R2R ladder network.